Okay, so now we're in section 3.3. The topic here is orthogonality. So back in the previous section, 3.2, we talked about the dot product and how we can use the dot product for a number of things, one of which was to determine the angle between two vectors. Now, later on in chapter 6, we're going to generalize the concept of the dot product to other systems. We call them vector spaces outside of Euclidean n space, and we're going to use that generalization of the dot product to come up with generalizations of all the things the dot product gives us in Rn, namely, norm of a vector, angle between vectors, distance between vectors, things like that. So in those cases, in those general cases, usually the angle between two vectors is not that important, except for one specific case, if that angle is 90 degrees. We know that if a vector, or if two vectors have a 90-degree angle between them, we would normally think of those as being perpendicular. The term we're going to use in this class is orthogonal. So again, if you have two vectors whose angle, where the angle between them is 90 degrees or pi over 2 radians, then we say that those two vectors are orthogonal. And it turns out that orthogonal vectors have a lot of interesting properties that are of value to us. But using this formula that we came up with in the previous section, relating the angle between two vectors to the inverse cosine of this this quantity involving the dot product in here, we know that the inverse cosine of 0 gives us pi over 2, or 90 degrees. So the only time that this theta will equal pi over 2 radians, or 90 degrees, is if this quantity is equal to 0, which will only ever happen if that dot product is equal to 0. So that gives us a alternative way of defining orthogonality. We say that two vectors are orthogonal to each other if their dot product is 0. And the benefit of that approach is that we can apply that concept to higher dimensional space, 4 space, 10 space, a billion space if you want, where you can't really visualize what a right angle looks like, but you can still have a meaningful concept of orthogonality. Now, oftentimes we aren't just interested in a specific pair of vectors being orthogonal. Sometimes we want to apply the term orthogonality to an entire set of vectors. So if you have a set of vectors and every pair of vectors in that set is orthogonal, then we call that an orthogonal set. So I'm going to illustrate that with this example here. Before we do that, though, note that because the dot product of any vector with the 0 vector is always going to be 0, then our definition of orthogonality would say that the 0 vector is orthogonal to every vector. And that's an important thing to keep in mind. Okay? So here we're going to do an example where we show that the set of standard basis vectors in R3 is an orthogonal set. Remember, your standard basis vectors are I, J, K, and I'll use arrow notation for those. Now, in order to show that this is an orthogonal set, I have to form dot products from every possible pair of vectors in this set. And because the dot product is commutative or symmetric, I don't need to compute I dot j as well as j dot I. Just one of those is good enough. So that means there's 3 pairs that I need to form. I dot j, I dot k, and j dot k. That's every possible pairing of vectors in this set. And it's really easy to show that these are all equal to 0. I'll do the first one, and then you should see pretty easily why the other two would be orthogonal as well. So I dot j, remember that's 1, 0, 0, dotted with 0, 1, 0, which is just equal to 1 times 0 plus 0 times 1 plus 0 times 0, which is clearly 0. Okay? If this were a problem on a test or something, I would want to go the full way of doing similar work for these two here. but since it's pretty clear that these are going to come out to 0, I'm going to just summarize that this way. So because every possible pair of vectors in this set has a dot product of 0, we would say that this is an orthogonal set. Okay. All right. Now, with this concept of orthogonality, we have some interesting ways of characterizing common graphs in 2 space and 3 space, namely lines in 2 space or 3 space and planes in 3 space. So let me start with the idea of a line. You've known how to graph lines since elementary algebra, but we haven't done it from the perspective of vectors yet. If you've been in Calculus 3, you may have seen this way of thinking about a line, but we're not assuming you've had that. So suppose we have this line in 2 space, so it's in the plane, and we know a couple of things about this line. One, we know one point on that line, call it P naught, and you give it coordinates x naught, y naught. And then we also have something that we're going to call a normal vector. A normal vector is a vector that's orthogonal to the line. Now, our definition of orthogonality was specifically defined in terms of vectors. 2 vectors are orthogonal to each other if their dot product is 0. So what does it mean for a vector to be orthogonal to a line? Well, in order to make that term usable here, I have to form a vector that's completely on that line. So what I do is I pick some arbitrary point on the line, call it P, and give it coordinates x, y. And then think of that as the terminal point of a vector whose initial point is the fixed point that we talked about, P naught. That initial point and terminal point, when joined by this vector, you can see that the vector would be completely on that line. And so we would say that the vector n, which I'm calling my normal vector, is orthogonal to this vector regardless of how we chose P. So that n, which we call a normal vector or simply a normal, being orthogonal to the vector P naught P would say that their dot product is equal to 0. Now, this creates an equation that basically defines this entire line. And the reason for that is because P was chosen as an arbitrary point. So any point on that line, when used to create this vector, would have to satisfy this equation, making this an equation for that line. And we call this a point normal equation, because in order to come up with it, you need one point on the line and a normal vector. Okay. Now, if we want to put this in a slightly more useful form, what I can do is put both n and P naught P into their component forms and perform this dot product. So n, we're giving that components a, b, and P naught P is a vector that comes from a known terminal point and initial point. So we can subtract x's and subtract y's to get the components of this vector. That would mean that this equation, after taking that dot product, would look like this. A times x minus x naught plus b times y minus y naught equals 0. This is the equation of a line. Now, this may not be the way that you're used to looking at the equation of a line, but if we simplify it somewhat, we can put it in a slightly more familiar form. If I distribute the a in, it's giving me an ax here, a by here, and a couple of constants. Remember, the x naught and y naught, those are from a fixed point, so those would be constants. And then if we combine all the constants into one constant and call that c, which we're doing up here, then that same equation can be written as ax plus by plus c equals 0. Now, an important special case of this equation of a line worth singling out is the case of a line that passes through the origin. So if this line from this equation passes through the origin, then that would imply that c equals 0. See if you can understand why that would have to be the case. So the equation reduces to just this: ax plus by equals 0 if we're talking about a line containing the origin. Okay? Now, moving away from lines and going to equations for planes in 3 space, we can see that the definition of a plane is actually going to look extremely similar to this. And we derive it in essentially the same way. Imagine we have a plane in 3 space, and here's just a little piece of the plane passing through the first octant. If you haven't had Calculus 3, you probably don't know what an octant is, but it's the analog for a quadrant in three-dimensional space. It's not important terminology for us, so don't worry about that. You can kind of see this little triangular piece of a plane, but that would extend in all directions. And just like the derivation for the point normal equation of a line, we're going to assume that we have some known point on that plane. It's a fixed point, P naught, with coordinates x naught, y naught, z naught. And then we're going to let P just be any arbitrary point on that plane. And as before, we give it, coordinates x, y, and then z because we're in 3 space. We're also going to assume that we know a normal vector, or we're given a normal vector for that plane. The normal vector is going to determine the orientation of that plane. And again, in order to make sense of the term orthogonal, because again, the normal vector should be orthogonal to the plane. To make sense of what it means for a vector to be orthogonal to a plane, we simply say, if we have any vector contained entirely in this plane, then n should be orthogonal to that vector. Well, p naught and p can be the initial and terminal points of this vector, this arbitrary vector, and n should be orthogonal to that, if it's orthogonal to the plane. So we're assuming all of these things. Okay? Now, once again, we can come up with the exact same point normal equation, but this time it represents a plane when we're in 3 space as opposed to a line in 2 space. And again, the reason for that is because this point, the terminal point of this vector, was chosen arbitrarily. So this could have been any point in the plane, and yet this would always have to be true. Our normal vector, ABC is what we're calling it, has to be orthogonal to this vector P naught P. So the set of all points that we could choose for P is exactly the set of all points that would have made this equation true. That means we're looking at the equation of a plane. Now, forming the dot product here with the plane gives us this equation. Notice the similarity between this equation and the equation for a line. We simply have this extra term here, c z minus z naught, still equal to 0. And also, as was the case with the line, we are going to single out the special case of the plane passing through the origin. So if the plane contains the origin, just like the case with the line passing through the origin, the constant term d would have to equal 0 in that case. So in the case where the plane contains the origin, we have a slightly simpler looking equation, ax plus by plus cz equals 0. Where again, remember the coefficients here, a, b, and c, are the components of a normal vector for that plane. Okay, so let's put this into practice with an example. Let's find an equation of a plane that's known to contain the point 1, -3, 0, and has normal vector n equals 1, 4, -3. This is about as straightforward as an example as we could do because it's really just a matter of plugging things directly in to this equation up here. Okay, so let's do that. If I plug everything in, a is 1, so I'm not even really going to write a 1. X minus x naught, which would be 1, plus 4, times y minus y naught, that would be y plus 3. And then minus 3 times z minus z naught, that's 0. Set that equal to 0. Now, technically, I could just leave my equation in this form. There is one downside to leaving the equation in this form, however. Remember, we were given a point on the plane, but there's an infinite number of points on this plane. And if we happened to be given a different point on the plane, I would have had different numbers showing up here, here, and here. So the equation would still be describing the same plane, but it would look different. So sometimes if we want to ensure that we get a more standard form for this equation, we go that extra step and distribute everything in combined like terms to get an equation of this type. Only one equation of this type will describe this specific plane. So let's think about that for a second. I'm going to have x plus 4y minus 3z, z. And then combining some constants, I'm going to get a 0 here, so there's nothing to consider. I'm going to have -1 plus, this will be a 12 here. So that's going to be plus 11 equals 0. Okay. either one of these is a valid equation for the plane, but on a test or something, just to make sure that we're all getting consistent answers, I will usually be asking for this one. All right? Okay. So one thing that we can point out now that we have an equation for the plane is a really important property of planes. And it's something that we're going to explore in more depth once we get into chapter 4 and we start talking about spanning sets. But we have some use for it in chapter 3 as well. Let's suppose that you have a plane with this equation. And notice there's no constant term here, or you could say the constant term is 0. So this would have to be the equation of some plane that's passing through the origin. If a plane passes through the origin, and if you have any pair of vectors that are parallel to the plane, and when we say parallel, another way of thinking of that is that the vectors are contained in the plane. Remember, let's come back to this picture right here. The vector p naught p was drawn in such a way that it appears that it's in the plane. But remember, you can take vectors and move them anywhere you want, and they're still the same vector, even if their position changes. So if I take this vector and sort of float it away from the plane, it's no longer going to appear contained in the plane, but it would be parallel to it. So whether I say these two vectors are contained in the plane or parallel to the plane, I'm talking about the same thing there. Okay, so let's suppose these two vectors are either parallel or contained, whatever term you want to use, in this plane given by this equation. Okay, what I want to show is that any linear combination of the two vectors that we just described, u and v, would also have to be contained in that plane, or would also be parallel to that plane. So to do that, let's pick some arbitrary pair of scalars, p and q, and form a linear combination, pu plus qv. Well, you can see that if I changed u and v into their component forms, multiplied the p and q in, and then did the addition, I would get this vector right here. Okay? Now, in order to verify that this linear combination is giving me a vector that's in the plane, I would have to show that this vector satisfies this equation. But remember, we identify vectors with points in space, specifically if they're position vectors. So if we think of this as a position vector, then the component form of this vector would correspond to the terminal point of this vector, and that should correspond to a point on that plane if it satisfies this equation. That means I can think of this as my x, y, and z, which gets plugged directly into this equation. Now down here you can verify the steps, but if you plug your components in for the x, y, and z for this equation, and distribute the a, b, and c, and then recollect terms based on which ones have a p in them and which ones have a q in them, factor the p and q out, this is what we have. Both of these expressions, AU1, BU2, or plus BU2 plus CU3, and this one as well, both of these expressions will equal 0 because U1, U2, U3 is the component form of the vector U, and we assumed U was in this plane, which means these should satisfy this equation. Well, this is what the left-hand side would look like after making those substitutions. So we get 0 here, 0 here. The whole thing comes out to 0, which means this vector also satisfies that equation. Okay. Now that should conform to some intuition. Suppose that we are looking at a plane like this, and let's suppose we have these two vectors, u and v, that are in the plane. I can see easily enough that if I were to scale the vector u, so call that p u right there, stretching the vector out is not going to take it out of the plane. If the original vector u is only this short or this long, multiplying it by the scalar stretched it out, I'm still within the plane after performing that scalar multiplication. Same thing if I multiply my vector v by some scalar q. qv would also still be in the plane because scaling a vector should not change whether or not it's in this plane. And then adding these two things together simply forms a parallelogram, and then creates the sum as the diagonal of that parallelogram. So that would be PU plus QV. But notice, if these two vectors are completely contained in the plane, then the entire parallelogram should also be contained in the plane, as should the sum of those two vectors making the diagonal. So that's an incredibly important property of this plane passing through the origin. Any linear combination of a pair of vectors in that plane will always still be in that plane. Okay, so we'll kind of see the importance of that later. All right, so I'm gonna work through this next topic in the next video. I'm just gonna introduce it here so we can see kind of what we're getting after. Oftentimes when you're talking about vectors in engineering or physics or one of the sciences, it can be helpful to decompose your vector into a couple of parts. And what I mean by that is find a different pair of vectors such that their sum is equal to the vector that we're actually interested in. So here's a basic example to help illustrate that. If you've ever studied projectile motion, which you should have if you've taken pretty much any physics class, engineering, or even, like when I teach pre-calculus, we talk about this. You can think of the initial speed of an object or initial velocity, which we usually call v0, as a vector. The length of the vector represents the magnitude, so the actual speed. The direction is exactly that. It indicates the direction that the object or the projectile has been fired or launched in. Usually when we analyze projectile motion using vectors like this, we take the initial velocity and decompose it into a horizontal component and a vertical component. And here we're calling those v0x and v0y. You can see that the sum of these two vectors would be this vector v0. You can see that it forms the diagonal there. Now the benefit of decomposing this vector into two parts is that the vertical vector can be interpreted as, or can be used to determine the height of this projectile at a given time, and the horizontal vector can be used in some formulas to determine the distance the object has traveled in whatever amount of time. So each of these vectors can be used for a different measurement of this object in projectile motion, which is why it's useful to have it decomposed into a sum of these two vectors. Now, in this particular case, these two vectors are also orthogonal to each other. And most of the time, if we're going to decompose a vector into a pair of vectors like this, it's usually going to be the case that we want them to be orthogonal to each other. It ends up simplifying a lot of the work that we do. So in the next video, we're going to introduce this idea of decomposing some vector in Rn, not necessarily in R2 or R3, but in Rn, into a sum of orthogonal vectors. And that's going to be the next video.